detach. Pop out chat. How do I move the chat next to the OBS instance? How is that done? Nope. There we go. Sounds like there's a perpetually boiling pot going on. Weird. Maybe it's just all the melting snow out there. All right. So I just finished that. So what am I solving today? I don't necessarily have a problem set yet, but I'm just reading my analysis textbook and maybe trying to prove some of the stuff in it. Morning Xanax, whatever, Zamaoan. All right. Although there are a few dangers to avoid, the algebraic limit theorem verifies that the relationship between algebraic combinations of sequences and the limiting process is as trouble-free as we could hope for. Limits can be computed from the individual component sequences provided that each component limit exists. The limiting process is also well behaved with respect to the order of operations. Okay. So we can assume that both of these limits go to certain values, and then for all a(n) greater than 0, for all n, then a is greater than 0. Okay. All right. Yeah, that's pretty self-explanatory. This first one, we've got just every term of the sequence is greater than 0, then what the sequence converges to will be greater than 0. That's kind of obvious. And then if all the terms of A are less than all the terms of B, then what A converges to will be less than what B converges to. Okay. If there exists a C in the real numbers for which C is less than all elements of B to the n, B sub n, so in other words, it's got like a lower bound. For all n, then C is less than what the sequence converges to. Okay. Similarly, if a to the n is less than C, so it's an upper bound. C is an upper bound of A, then what A sub n converges to is less than C. Okay. All right. That seems reasonable. a to the n, or an greater than 0 does not imply a greater than 0, although it does work for greater than or equal to. That's interesting. Why would that be? Why would that be? So it's got to include 1/2, 1/4, 1/8, 1/16. Right. Right. Yeah, I see. Because that converges to 0, but none of the individual terms are 0. Yeah. Well put. Okay. So the proof of 1, we will prove this by contradiction. Thus, let's assume that a is less than 0. Okay. The idea is to produce a term in the sequence that is also less than 0. To do this, we will consider the particular value of epsilon equals absolute value of a. The definition of convergence guarantees that we can find an n such that a to the n minus n, or the absolute value of it, is less than that epsilon value, which is absolute value of a, for all n greater than or equal to big N. In particular, this would mean that a sub n minus a is less than absolute value of a. I mean, yeah, okay. Which implies that a to the n is less than 0. This contradicts our hypothesis that a to the n greater than 0. Okay. That's quite simple. Sequence. Yeah. I'm looking for it's also less than 0. Where is the assumption that a sub n is greater than or equal to 0? Hello, Big Pepe. No, I'm not a first year. And yeah, this is basically maths documentation. All right. And then they draw a little picture. Okay. That's weird. It's like backwards from what it usually is. Okay. I kind of get that proof. Not especially, but moving along. The algebraic limit theorem ensures that the sequence BA, or Bn minus An, converges to B minus A. Because Bn minus An is greater than or equal to 0, we can apply part 1 to get that B minus A is greater than or equal to 0. Okay. Word about the idea. Oh, this is the proof of 3. The proof of 3 is pretty damn obvious, apparently. word about the idea of tails is in order. Loosely speaking, limits and their properties do not depend at all on what happens at the beginning of the sequence, but are strictly determined by what happens when n gets large. Sure. Changing the value of the first 10 or 10,000 terms in a particular sequence has no effect on the limit. Theorem 2.3.4, part 1, for instance, assumes that all terms are greater than or equal to 0 for all n. However, the hypothesis could be weakened by assuming that there exists some point n where n greater than 0 for all n greater than n1. The theorem remains true, and it is in fact the same proof is valid, with the provision that when n is chosen to be at least as large as n1. So that's pretty much just saying, like, that's if the beginning is fucked up, then it's okay. You just have to also specify that the beginning is fucked up, but we just assumed it's nice so we could write it out well. Guys, what do you mean performative reading? I just have to read this textbook for this class. Isn't saying performative reading, like, kind of dangerous? Like, because, I mean, like, isn't anything you do performative? Okay. In the language of analysis, when a property such as non-negativity is not necessarily possessed by some finite number of initial terms, but is possessed by all terms in the sequence after some point n, we see that the sequence eventually has this property. Theorem 2.3.4, part 1, could be restated. Convergent sequences that are eventually non-negative converge to non-negative limits. Yeah. So basically we just omitted that. Alright, here's some exercises. No, I don't like div portfolios. I actually hate them. You ever considered, like, working at a gas station? Like, at least that would be easy work to get. Plus, what does money really matter? Squeeze theorem. I'm studying analysis, but we just finished limits. I was just kind of reviewing iterated limits. Okay. Doubly indexed array where m and n are in the natural numbers. What should the limit of m and n goes to infinity of mn represent? Iterated limits. What? Define to mean for all epsilon there exists an n such that if both m and n are greater than n, what is this even asking? Oh, and compute the iterated limits. Assume n is constant and compute the limit for m, and then the limit for n. What are your credentials, Poseidon? I don't know who to trust. Yeah, I mean, I do take notes in my own, but I like to see how the textbook does things because they lay it out clearer. Stephen Abbott is really good too. You know, I'm not sure I trust you. Would you rather you can only use like the biggest, heaviest Claude model and you have to pay out of pocket to ask like really simple questions and it's going to do like maximum reasoning, or you can only use like the tiniest open source Quen model and to do like agentic coding tasks? Thanks, Pokey Tiss. Okay. Let a mn equals 1 plus mn. Does the limit, the iterated limit, exist in this case? Do the two iterated limits exist? Do these three values compare? Answer these same questions. Oh, no. You know, none of this was on my homework, so I'm assuming it's not going to be on the exam, so probably not even worth thinking about. I also think from E we're going to see that that all three must be equal. So that would help in D. All right, I'm just, I don't know. I'm waiting for my homework to come out and just skimming in the meantime. Monotone convergence theorem and a first look at infinite series. Okay. Convergent sequences are bounded. The converse statement is certainly not true. So unbounded series are divergent? Or no, that would be the contrapositive. This is just divergent series are unbound. Whatever. It is not too difficult to produce an example of a bounded sequence that does not converge. Oh, yeah. I mean, yeah, you could just give like an oscillating series. On the other hand, if a bounding sequence is monotone, then it does in fact converge. I mean, it's always increasing or decreasing. Oh, what's up, Johnny? If a sequence is monotone and bounded, then it converges. So let a sub n be monotone and bounded. To prove it converges using the definition of convergence, we're going to need a candidate for the limit. That's so general. Let's assume the sequence is increasing. The decreasing case is handled similarly, and consider the set of points A sub n. Okay, so just like every point of the sequence. By assumption, the set is bounded. So we can let the supremum equal S. Seems reasonable to claim that the limit equals the supremum if it's increasing. Yeah. Sure does. And there we go. To prove this, let epsilon greater than 0. Because S is the least upper bound for, it's the supremum. S minus epsilon is not an upper bound. So there exists a point in the sequence, A, N, such that S minus epsilon is less than A, N. Now, the fact that an is increasing implies that if n is greater than or equal to big N, then an is less than little an. Yeah. Man, I'm tired. What's the Norwood Reaper? Okay, then we have this inequality. S minus epsilon is less than a to the n, is less than or equal to a to the n, is less than or equal to the supremum, is less than the supremum plus epsilon. What? How'd they get that implication? Oh wait, yeah, that's pretty obvious. They just subtracted S. Okay, that wasn't that bad. What's Midna's lament theorem? You guys ever think maybe I should just like pick religion as a major or something? What do you mean? I'm not starting to bald. There's like no history of male balding in my family at all. I think the fact that you have Looksmaxer in your username says a lot. Alright, the monotone convergence theorem is extremely useful for the study of infinite series, largely because it asserts the convergence of a sequence without explicit mention of the actual limit. That is really nice. You can just not calculate the limit. No, you can't play tic-tac-toe on my forehead. I'm renting it out for a chess tournament later. It'll be occupied. Let B of n be a sequence. An infinite series is a formal expression of the form so just add up all the partial sums, yeah. This is like kindergarten shit. real analysis convergence. Whether or not we can find an upper bound. Is less than whoa, what's going on here? Okay, so this line I follow, they convert the inequality, and then they get this, and then they do a little something like this. They break all these down. 1 minus 1/2, 1/2 minus 1/3, 1/3 minus 1/4, all the way up until they break down those two things. And then all the factors are canceled. Oh, this 1/2 and this 1/2 are canceled. This 1/3 and this 1/3. Gotcha. All the way up until this. Yeah, that is really nice. This is Understanding Analysis by Stephen Abbott. He's also from Vermont, fun fact. He was at my school the other day. I'm 12. Yeah, that's a very nice trick. Very nice trick. I don't know that I would recognize that. 2 is an upper bound for the sequence of partial sums. So by the monotone convergence theorem, this is going to converge to sum for the moment unknown limit less than 2. What's it going to converge to? That's the question. It's less than 2. But what is it? I wonder what subject. Oh. Okay. Finding the value of this limit is the subject of section 6.1 and 8.3. Damn, there's 2 big gaps there. All right. The harmonic series. I've seen this one before. So again, we have increasing partial sums. Yep. Checks out. That upon naive inspection appear as though it may be bounded. However, 2 is no longer the upper bound because at S of 4 we hit 2. So, I mean, yeah, however 2 is no longer a bound. Okay, similar calculation shows that S of 8 is greater than 2.5. So we can see in general, okay, they're grouping it into that's interesting. That is a very interesting way to group that. No way it converges to pi squared over 6. That can't be true. I'm gonna need to see proof of that. So this is very clever, actually, like, arranging this. No, it doesn't. I literally don't buy that. So grouping like this is very clever, and then upper bounding, like taking this, like this fifth and this third, and then producing something smaller, and then we get 1 plus a half plus a half plus a half. We get k halves, and that is unbounded. So it eventually surpasses every number on the positive real line. Even like a really, really big number? Like, what about like a billion? Basel problem. We'll see. That'll probably come up. They'll probably prove it. And okay. Elementary. I think. Or introduction to analysis. What is this called? Understanding analysis. Okay. How do you pronounce this guy's name? Cauchy? 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 Cauchy. The third one you see. Cauchy, Cauchy, Cauchy. Is it Cauchy or Cauchy? Cauchy. 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 Is it Cauchy or cooler? Cauchy. 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 Okay, I'm just saying Cauchy. Alright. Who is Cauchy? Cauchy. Was that a mathematician? Or just like, that's what they named this? Okay, the previous example is a special case of a general argument that can be used to determine the convergence or divergence of a large class of infinite series. The Cauchy convergence or condensation test, sorry. It's a noun. Cauchy is one of the goats. You know, there are too many goats. There are just so many great mathematicians. Suppose Bn is decreasing and satisfies being greater than 0. Okay. So it's decreasing, but everything is greater than or equal to 0. Then for all n, then the series converges if and only if the series, what? The Cauchy condensation test. So that was out of left field. If and only if, so we staple 2 to the n to this series, but the series is also what? I guess I kind of get that. That's really interesting, though. Yeah. Oh, he was an engineer and physicist. Okay. What's up, Wiss? So this is basically saying the condensation test that even if we staple 2 to the n to this bad boy, then as long as our indexing is also moving at the speed of 2 to the n, we're chilling. Yeah, I think about that sometimes too, Poseidon. Like, imagine just how many damn hours it probably took to come up with stuff. And, like, I was reading about the definition of convergence earlier. Like, they came up with that definition, like, after a long time of like, formalizing the intuition. Like, a lot of these things are just years and years and years and years. Hours. Oh, yeah, the hidden part? Yeah. Well, I'm just looking at this. Oh, I guess we're looking at the proof now. Okay. Yeah. First, assume that that bad boy converges. Theorem 2.3.2 guarantees that the partial sums t sub k are bounded. Okay, partial sums are bounded because this converges, all of the partial sums are bounded. That is, there exists an m greater than 0 such that the sum is less than the partial sum up to some k is less than m for any natural number. We want to prove that this bad boy converges. Okay. Because it's greater than 0, did we assume that? We did, yeah. Okay. Because it's greater than 0, we know that the partial sums are increasing. That doesn't seem like the most intuitive thing in the world to me. How do we know the partial sums are increasing? I'll do number theory another. I have an exam actually coming up. Because Bn is non-negative, so the partial sums are increasing. Oh, yeah, duh. Yeah, because if they're non-negative, the more b to the n we add, the bigger, and the more terms we add. Duh. Obviously. We know that the partial sums are increasing, so we only need to show that the partial sum up to m, up to little m, is bounded. Okay. if we show like the maximum partial sum is bounded, then that'll just imply that, well, like an arbitrary partial sum is bounded will imply that the sequence converges. Okay. M, and let K be large enough to ensure M is less than. Okay, where's our K at? What is K? K is just some natural number. Or we... Oh, no, fix a K. Oh, okay. I got confused by that early part. We're just choosing a K. Alright, so we got M, and then M is less than 2 to the K plus 1 minus 1. Then the partial sum of an arbitrary... Okay. Yeah, that's clever. And we can do that because those are increasing and it won't flip the inequality. So that's some next level algebraic operation right there. Respect that. Look at how weird this PDF reader selection is. Okay, so we just slap those into the partial sums. And then we say that that's going to be equal to B1 plus B2 plus B3 all the way up. But we're grouping those to B sub 2 to the K to B sub that. So this trick is like really, this is really getting me going. I'm really enjoying the way that they're doing this. Like they've got like big chunks of, like they're chunking up the infinite series like this, and then since we know that they're like, this is the smallest element, just replacing all of those and then getting a greater than. Well, these are bigger technically. This is a bigger thing. That's just like so well done. Oh, and then the algebra all simplifies because we get this partial sum, TK. And did we say that was bounded originally? That's very nice. I'll whip out the pen and paper if I gotta. Wait, is TK bounded? How do we know that? Oh, yeah. Because of theorem 2.3.2, TK is bounded, just because we know that converges. And then we just say that that's equal to TK. And thus, an arbitrary partial sum is less than TK, which is less than M, and the sequence is bounded. By the monotone convergence theorem, it's increasing and bounded. We assumed it was increasing. Then sum of Bn converges. And then the other way is similar to exercise 2.4.5. The details are going to be required. Man, I hate when they do that. Just show me how to do it. The other thing is bounded because it converges by assumption. How to become math. You don't understand the inequality conversion? Like right here. Well, because each of the terms is increasing, like this B3 or this B2 is less than this B3, which means this overall thing is less than this. Which actually it seems like the inequality would be the other way around. But no. Because that's equal. But if we... Yeah, why is that not the other way around? Do you mean greater? That's what I'm confused about. It's the other way around. B of n is decreasing. Oh, it is? Because that would explain it. But is B of n decreasing? Oh yeah, it literally says it right there. I was under the impression it was increasing, but I guess that was from the last time. All right. So maybe I'll prove that in the exercises. Once we get to the exercises, which looks like it's impending, I'll have to whip out some pencil and paper, some nonsense. No. Why did I pick this damn major? All right, the series 1 over n to the p God damn it. Why am I not a history major? The series 1 over n to the p converges if and only if. This is straight up a corollary. What's it a corollary to? Oh, a corollary is like a lemma, but afterwards, right? That's like by the way, this also. A rigorous argument for this corollary requires a few basic facts about geometric series. Proof is requested in exercise 2.7.5. Cool. Yeah. Alrighty. All right. It's over if you're not doing scheme theory by 12. Yep. Okay. All right, this is interesting. Probably worthwhile to practice this. What's scheme theory, by the way? I'm going to look that up, actually. Scheme theory. Scheme. Generalizes algebraic varieties to include arbitrary commutative rings, enabling the study of geometry over integers with nilpotent elements. Yeah, I understood that scheme. Oh, it's an algebraic geometry thing. I'm really interested in this, something I didn't pick this major, but unfortunately, you are less respected in society if you study arts. Pure or applied math. You're less respected. A scheme is a structure that enlarges the notion of algebraic variety. Uh-oh. I can't read this without going down like 40 other links. Central objects in study, a subfield of mathematics, classically whether real or complex numbers. Multiplicities. $1960. That's quite recent as far as math goes. And it was in French. Scheme theory. Alright, the more you know. Just give me a K and R in my C compiler. Wait, I thought what's his name? Cauchy? I thought Cauchy was the goat. There can't be multiple goats. Greatest implies that there's only one. Actually, I'm gonna just like skim through this. I don't really feel like doing exercises at the moment. I'm lazy this afternoon. Recursively, I got like a ton of recursively defined sequences in the homework. And recursively defined sequences are interesting because like they kind of tell you the relationship of how the terms are changing, but it's also like a little harder to sometimes like rearrange them. Yeah, but if he's the goat, then like I feel like there are earlier goats. Like, what about Euclid and Euler and Newton? Like, there are plenty of people who churned out pretty amazing things. What's wrong with Newton? I've got clearance for Gothendik is the Grothendieck unpublished notes on the BNF. Hit me up if you want the scans. Yo, that's awesome. Crazy you're hanging out in an undergrad math stream. Whoa, that's spicy. Oops, did my PDF reader crash? Nope. So those are interesting. We use the axiom of completeness to prove the Archimedean property of R. What's the Archimedean property? That's just like it has to do with sealing. Show that the monotone convergence theorem can also be used to prove the Archimedean property without making use of the axiom of completeness. It's unfortunate that the axiom of choice is also called AOC. For any real numbers, there exists a natural number such that n is greater than x, meaning the set of natural numbers is not bounded above. How do we know, though? Like, what if there's just like a bigger number we haven't checked? There's no way they can check all the numbers. There's just not enough time in the day. This field is really weird. Monotone convergence theorem to supply a proof for the nested interval property that doesn't make use of the AOC. Walk. These two results suggest that we could have used the monotone convergence theorem in place of the AOC as our starting axiom for building a proper theory of the real numbers. There's no way. There's no way the axiom of completeness. How is that possible? The Archimedean property of R to prove how does that even make sense? The monotone convergence theorem could also be used to prove the Archimedean property without the axiom of completeness. It's so different, though. What? That's not... That can't be true. If you have that all bounded monotone sequences converge, then there are no holes. Oh. Yeah, I guess that somewhat does make sense, because, like, if you, like, said towards a contradiction that it doesn't imply the Archimedean property, like, you could have, like, a bounded increasing sequence that just, like, doesn't converge to anything, then there would be a hole before the bound, and that doesn't really make sense. Density argument? What's a density argument? Since you can construct a sequence converging to any natural. You can make a sequence of rational numbers that converges to square root 2. So it converges in R but not in Q. Yeah, that's interesting. No, I've never studied the density of Q. Yeah, 2 point, yeah. And then use the monotone convergence theorem to supply a proof for the nested interval property. What's the nested interval property? Why does clicking on this like send me to... I swear I can't click on that without it. Okay, clicking isn't gonna happen. Nested interval property. Is that really like, could you build real analysis using the monotone convergence theorem instead of the axiom of completeness? Taking small but fixed steps, you eventually surpass all fixed real numbers. Okay. And what's the nested interval property? I can't click on that, so... Sequence of non-empty closed or bounded intervals that are nested has a non-empty intersection. Okay. Yeah. Yeah. Constructive analysis or analysis with the hyperreal so you avoid limits entirely. What's a hyperreal? Dedekind cut. What is a hyperreal? Hyperreal, extension of the real numbers that rigorously incorporates infinitesimal and infinite. What? Infinitesimal? Infinite numbers. No way. Does this mean you can just like have infinity and then just like throw it around in algebra? Extension of the real numbers. Hyperreal is awesome. Good job, Edwin. The transfer principle. States that all statements of some language that are true for some structure are true for another structure. Holy shit. God, I love how, like, just insane math is. True first-order statements about R are also valid in hyperreal. Holds for hyperreals. Or alternatively, smooth infinitesimal analysis. Subtheory of synthetic differential geometry. Oh my god, what the fuck? This is outrageous. So this is like the infinity. This is the biggest number. And you can just keep adding 1 and everything is less than it. Oh, you said analysis. And as the symbol infinity is, for example, in limits of integration. It's true for the real numbers, and it is the form required by the transfer principle, so it is also true for the hyperreal numbers. Shows that it is not possible to use a generic symbol such as infinity for all the infinite quantities in the hyperreal system. Infinite quantities differ in magnitude from other infinite quantities, and infinitesimals from other infinitesimals. Yeah. Similarly, the casual use of 1 over 0 equals infinity is invalid, since the transfer principle applies to the statement that 0 has no multiplicative inverse. Rigorous counterpart of such a calculation would be that epsilon is non-zero infinitesimal. Where do you even learn about this stuff? All this comes from model theory. Is this just what math grad school is like? Relationship between formal theories. This is so meta. Collection of sentences in a formal language expressing statements about mathematical structure and their models. The aspects investigated include the number and size of models of a theory, the relationship of different models to each other. What? Inner versus outer models. Undergrad logic. Is actually very robust and correct, although most mathematicians know nothing about it. Huh. Math is really weird, dude. Yeah. How hard is it to understand Gödel's incompleteness theorem? Is that like a beefy ass proof? Alright, moving right along. Arithmetic geometric mean. Explain why square root xy is less than x plus y over 2 for any two positive numbers. Huh. Geometric mean is always less than the arithmetic mean. But they both, taking like a repeated sequence of arithmetic means and geometric means are the same. They converge to the same thing. That's really weird. X is less than y1. A minus b squared is greater than or equal to 0. Xn is increasing and yn is decreasing. All right. Bolzano-Weierstrass theorem. Wait, I'm curious about that Gnarvaro. In saying that today all these problems are solved by LLMs, I do not think we'll have human mathematicians much longer. Yeah, Ciara, Siasura, I agree. True. Doing math is a good mental exercise. All right. Example 245, we show that the sequence of partial sums of the harmonic series does not converge by focusing our attention on a particular subsequence, S2
2 to the k of the original sequence. For the moment, we'll put the topic of infinite series aside and more fully develop the important concept of subsequences. Let a to the n, or a sub n, be a sequence of real numbers, and let n1 less than n2 less than n3, etc. be an increasing sequence of natural numbers. Then the sequence is called a subsequence of a to the n and is denoted by onc, where k and n indexes are subsequent. Wow, yeah. Okay.
Notation. Notice that the order of the terms in a subsequence is the same as in the original sequence, and repetitions are not allowed. Sure. So if a to the n equals basically the harmonic series, then are examples of legitimate subsequences, whereas going out of order and duplications are not. Simple enough. Subsequences of a convergent sequence converge to the same limit as the original sequence. Really? Okay. All right. Before I look at that, I kind of want to imagine how I would prove it. That subsequences converge to the same limit as the sequence that they're a part of. Yeah, how would you show that? I mean, they could converge if you say that they don't converge to the same thing and then try to derive a contradiction. Maybe. I mean, I feel like intuitively I'm still like, what does it mean for a subsequence to converge necessarily? Subsequences of a convergent, like how does a subsequence, like, okay, so we assume that a to the n converges to a, and that onc be a subsequence. Given an epsilon greater than 0, there exists an n such that a to the n minus a is less than epsilon whenever n is greater than n. Because nk is greater than k for all k, the same n will suffice for the subsequence.
This seems like just... It's like so simple. It's like it feels wrong. It feels incomplete. In the reals, a sequence converges if and only if it's Cauchy. It's trivial. What's up, Alex? Sequence converges if and only if it's Cauchy, so the terms get infinitesimally closer. This helps you mentally think about what a convergence sequence looks like. Yeah, but a convergent subsequence, like, it makes sense if you're ripping out the elements, ripping out certain elements, but like, what does it mean for... I guess I see what it's saying, yeah. Yeah, the same n will suffice for the subsequence. I don't... That's just like a little janky. It's like, oh, what's up, Vladimir? It's just like, it's literally convergent. And the subsequence is a subsequence, so it also converges. Yeah, this not too surprising result. Yeah, that's what I'm saying. Has several and somewhat surprising applications. It is the key ingredient for understanding when infinite sums are associative. We can also use it in the following clever way to compute values of some familiar limits. All right, we're going to see what they mean by that in a second. What is theorem? You should think of a subsequence as a picking out a sunset of the natural numbers. Proof sequence converges if and only if it's Cauchy. You need that theorem here. So a sunset of the natural numbers. Subsequence is picking out a subset of the natural numbers. All right. I mean, I've seen the Cauchy proof before. I want to see how they... Okay, so the sequence b to the n is decreasing and bounded below because they say it is. The monotone convergence theorem allows us to conclude that b to the n, b to the n converges to some limit satisfying b is greater than that limit, which is greater than or equal to 0. Okay. To compute L, notice that b to the 2n is a subsequence. So b so it also converges to the same limit. But that's the same thing as b to the n squared, or bn times bn. So by the algebraic limit theorem, that equals L squared. Because limits are unique,
L squared equals L, and thus L equals 0. Wow, that's pretty clever. And 1 isn't going to work because, yeah, B is bounded. That is pretty clever. I'll give them that. Without much trouble, exercise 257, we can generalize this example to conclude b to the n approaches 0 if and only if -1 b yeah, that's just what I said. We're quite sure that this does not converge to any limit. That's a subsequence, and that converges to 1/5. Is a different subsequence and converges to -1/5. Because we have two subsequences converging to two different limits, we can rigorously conclude that the original sequence diverges. In the previous example, it's rather easy to spot a convergent subsequence of 2 hiding in the original sequence. For bounded sequences, it turns out that it is always possible to find at least one such convergent subsequence. That's the Bolzano-Weierstrass theorem. Bolzano. This theorem is a banger.
Okay. Every bounded sequence contains a convergent subsequence. All right, let's see why that's true. Every bounded sequence contains a convergent subsequence. A to the n, a sub n, a n. How do you say that? An? The W, big W analysis. Proof is very combinatorial. Okay. Let an be bounded sequence so that there exists an M satisfying that absolute value of n is less than or equal to M for all n in M. So M is our upper bound. Bisect the closed interval -mm into the two closed intervals. Okay. The midpoint included in both halves, naturally. And the midpoint is 0. Now it must be that one of these closed intervals contains an infinite number of the terms of the sequence. It must be that one of these halves. Select a half for which this is the case and label that interval as I sub 1. Then let A sub n1 be some term in the sequence A sub n satisfying A sub n in I. Okay, and this is the picture.
And by the picture, I mean, next we bisect I1 into closed intervals of equal length. So we bisect again. And let I squared be half that again contains an infinite number of terms of the original sequence. Because there are infinite number of terms from a to the n to choose from, we can select an2 from the original sequence with n2 less than n1 and choose an2 in I2. We construct the closed interval ik by taking half of ik minus 1, containing an infinite number of terms of an, and then select nk minus 1, all the way down to 1, so that, oh, wow. Wow, that's really smart. That is wicked smart. We want to argue that that's a convergent subsequence, but we need a candidate for the limit. So the sets I subset I2, subset I3, dot, dot, dot. I1 subset I2. Oh, the subset symbol is going the other way than I'm used to. Okay. Yeah, that makes sense. Form a nested sequence of closed intervals. By the nested interval property, there exists at least one point contained in every ik. This provides us with a candidate we're looking for. Oh my god, why are these people so smart? Who thought of this shit? Holy shit. That's fucking awesome. This provides us with the candidate we're looking for. Just remains to show that the onc converges to x. So then we show convergence with an epsilon greater than 0 by construction. The length of ik is m, which is the upper bound, times 1/2 to the k minus 1, which converges to 0. And because we just keep dividing by 2 over and over again. This follows from example 2.5.3 and the algebraic limit theorem, because the algebraic limit theorem, do they mean like we're multiplying this by m, but wow. Subsequences and the Bolzano-Weierstrass theorem. Wait. Okay, which converges to 0. choose an n so that k, this is hurting my eyes. Do we have dark mode? Nice. Oh, there we go. Hopefully nobody minds. Choose n so that k greater than n implies the length of ik is less than epsilon. Because a and k and x are both in ik, it follows that... Oh, jeez, that's smart. Oh my god. Oh, did not mean to hit that. You can see the, like, light in the room visibly darken. Oh my god. Does every key toggle the dark setting? Yeah, apparently. So if I move... God damn. This dark mode is calculated like per page. Okay, I'm just not using it. That's just like so damn smart. So choose, I'm still trying to like understand the last part of this though. Choose an n so that k greater than n implies the length of ik is less than epsilon. So basically we're just cranking up the divisions all the way down until the divisions in half are less than the epsilon, less than any epsilon that we're given. And then we're going to have, because of the nested interval property, we have our limit is going to be in there, in that really small thing. And a to the n sub k. Why is a to the n sub k there? I mean, yeah, we want to show it converges, but I'm wondering why we know that it's in the interval. If you half that again contains an infinite number of the original sequence, because there are an infinite number of terms to choose from, we can select an a n sub 2 from the original sequence. With n2 greater than n1. Oh. we put it in there, and we construct each interval by throwing, okay, yeah. I see. Why can't I scroll? There we go. This PDF reader is so janky. Bolzano-Weierstrass. All right, I want to skip over the exercises for now. Cauchy criterion. So this is basically just that the elements get arbitrarily close to each other. And then convergence is just with some number A. And these imply each other, I guess. So we've discussed the definition of convergence asserts that given an arbitrary positive epsilon, right, they're closer. Spoil the surprise. Yeah, we're going to argue that these are the same. Somewhat like the situation with the monotone convergence theorem, in that we will have another way of proving that the sequences converge without having any explicit knowledge of what the limit might be. Every convergence sequence is a Cauchy sequence. This is not a super long proof. Assume xn converges to x. Prove that xn is Cauchy. We must find a point in the sequence after which x sub n minus x sub m is less. And this can be done using the triangle inequality in exercise 2.6.1. Okay. So, DIY. But the fact that every Cauchy sequence converges is not obvious. You really have to use the completeness of the reals. This is the difference between classical and constructive reasoning. What do you mean constructive reasoning versus classical reasoning? Do I have water? Like, what is... Constructive does not use the law of the excluded middle. Everything true to be computably so. Converse is a bit more difficult to prove, mainly because in order to prove that a sequence converges, we must have a proposed limit for the sequence to approach. I mean, unless you use the unless it's bounded and monotone, we must have a proposed limit for the sequence to approach. We have been in this situation before. I called it, I knew it. And the Bolzano-Weierstrass theorem. Our strategy here will be to use the Bolzano-Weierstrass theorem. This is the reason for the next lemma. Okay. There are also a lot of not true. You mean true? Not true. State for the things that you can't computably show to be true and computably can show to not be false. Can't computably show to be true and computably can show to not be false. No, I'm lost AF. Alright, Cauchy sequences are bounded. Given epsilon equals 1, there exists an n such that our two little guys, our two candidate points past n, are less than that epsilon of 1. Oh, and we know that because this is Cauchy. Okay. Thus, we must have x of n less than x of n plus 1 for all n in n. So it follows that m is the max, and we can just say that's the bound. Yeah. Yeah, not P is no longer automatically the same as P. No. That's unnecessary. What is this book? That's the book. Yeah, all this math and computer science stuff is just so damn complicated. Yeah. Keanu dude. Stephen Abbott. He came to my university the other day and put on like a play about math. It was pretty weird. But he wrote a good textbook. And then we got that a sequence converges if and only if it's a Cauchy sequence. For this direction, we start with the Cauchy sequence xn. Our lemma 2.6.3 guarantees that it's bounded. So then the Bolzano-Weierstrass theorem, we can produce a convergent subsequence.
The idea is to show that the original sequence x sub n converges to the same limit. Once again, we will use a triangle inequality argument. We know the terms in the subsequence are getting close to the limit x, and the assumption that xn is Cauchy implies the terms in the tail of the sequence are close to each other. Thus, we want to make each of these distances less than half the prescribed epsilon, and then if you do that, you can combine them. Classic trick. Boom. I learned analysis from Rodriguez, MIT. His book is also really good. I basically wrote down all the stuff he writes on the board and solved all the problems in the book. Took me damn near 6 months, but really rewarding. That's really impressive, Keanu, dude. You did that on your own? I also wonder, just to like ask for meta advice from grad students in here and stuff, like a lot of the time I like to study like off camera just because like I don't want to fully rely on other people, but like there are times when like I just will not get a proof after like 2 hours of trying, and then I just look at it and I wonder if, I mean, I've heard that's somewhat typical of analysis sometimes, like you just, certain tricks that they use in analysis are just like really damn confusing, or not confusing, but like unintuitive. I don't know, like there was a problem that used Bernoulli's inequality, which is pretty common, but or like I just wouldn't necessarily think strategically giving up is a wise thing to do. Yes, it feels like
2 hours on the low side for giving up. Yeah, this math just takes like a while to understand. Quantum physicist, I can assure you that I'm lying about my profession. Yeah. All right, I have to get to class pretty soon, so I'm going to end the stream.